Good day viewers. I am here to explain to you the key concepts regarding particle-wave duality and the uncertainty principle. Shall we begin? Wave-particle duality. Wave-particle duality is the concept in quantum mechanics that every particle or quantic entity may be partly described in terms not only of particles, but also of waves. It expresses the inability of the classical concepts particle or wave to fully describe the behavior of quantum-scale objects. On the basis of experimental evidence, German physicist Albert Einstein first showed in 1905 that light, which had been considered a form of electromagnetic waves, must also be thought of as particle-like, localized in packets of discrete energy. The observations of the Compton effect in 1922 by American physicist Arthur Holly Compton could be explained only if light had a wave-particle duality. Compton explained and modeled the data by assuming a particle nature for light and applying conservation of energy and conservation of momentum to the collision between the photon and the electron. The scattered photon has lower energy and therefore a longer wavelength according to the Planck relationship. At a time in early 1920s when the particle nature of light suggested by the photoelectric effect was still being debated, the Compton experiment gave clear and independent evidence of particle-like behavior. French physicist Louis de Broglie proposed in 1924 that electrons and other discrete bits of matter, which until then had been conceived only as material particles, also have wave properties such as wavelength and frequency. Later in 1927 the wave nature of electrons was experimentally established by American physicists Clinton Davison and Lester Germer and independently by English physicist George Paget Thomson. Remember that particle-wave duality tells us that every single entity has both particle and wave characteristics. These has been proven by experiments by different people. The uncertainty principle. The uncertainty principle, also called the Heisenberg uncertainty principle, or indeterminacy principle, articulated, 1927, by the German physicist Werner Heisenberg, states that it is impossible to know simultaneously the exact position and momentum of a particle. That is, the more exactly the position is determined, the less known the momentum, and this principle is not a statement about the limits of technology, but a fundamental limit on what can be known all about a particle at any given moment. This uncertainty arises because the act of measuring affects the object being measured. The only way to measure the position of something is using light, but, on the subatomic scale, the interaction of the light with the object inevitably changes the object's position and its direction of travel. Of course, once a measurement of the particle is made, a single momentum is observed. But, like fuzzy position, momentum before the observation is intrinsically uncertain. This is what is known as the uncertainty principle, that certain quantities, such as position, energy and time, in its purest form, the uncertainty principle states that accurate knowledge of complementarity pairs is impossible. For example, you can measure the location of an electron, but not its momentum, energy, at the same time. Mathematically we describe the uncertainty principle as the following, where x is position and p is momentum. Delta x delta p is greater than or equal to h bar over 2. This is perhaps the most famous equation next to E equals mc2 in physics. It basically says that the combination of the error in position times the error in momentum must always be greater than Planck's constant. So, you can measure the position of an electron to some accuracy, but its momentum will be inside a very large range of values and vice versa.